So in this video, I'm going to describe something called a Poynting vector. The Poynting vector is going to describe how the power will flow in an electromagnetic wave. Since we've already established that any wave must be carrying energy with it, and that energy is moving, that's going to imply a transfer of energy or a rate of motion of energy, and that will be defined as power. So there's two pieces to this lecture. In the first piece, I'm going to give a quick recap of wave propagation from the last couple lectures, condense everything and pick out the equations that actually matter. And then in part two, we're going to connect that to the power and energy flow, which we call the Poynting vector. So quickly, let's do the recap of wave propagation. Now, the four most important equations that sort of define most of electromagnetics are called Maxwell's equations. They are named after James Clerk Maxwell, who was the first to compile them, and he added one key term from which he postulated the existence of electromagnetic waves resulting from electric fields and magnetic fields, although they were not presented in the form that we now have mathematically. That was done later by someone else named Oliver Heaviside. So there are four Maxwell's equations. The first is that the divergence of the electric flux density equals the charge density. In words, that is that the electric flux lines will start at positive charges and end at negative charges because the divergence represents the outward flow of field lines from a given location, and a negative divergence would be an inward flow into a given spot. The equivalent for the magnetic flux density, or B, would be that the divergence of the magnetic flux density must equal to 0. In part, this makes sense because there's no such thing as magnetic charges, so there's no equivalent to put there. But other than that, there is a symmetry between the electric field and the magnetic field. All right, so now we have two of Maxwell's equations that relate to the curl. And the first is that the curl of the electric field, or the swirliness of the electric field, is equal to negative time derivative of the electric flux density with respect to time. This is another way of saying that electric field lines are going to be swirling around the time variation of the magnetic flux lines, not the magnetic flux lines themselves, but specifically how they are changing. If magnetic flux lines are changing, there's a vector associated with how it's changing, and magnetic field lines will swirl around it. In particular, you can use the right-hand rule to figure out how the electric fields are swirling, but the key is there's this negative sign, so you actually have to flip it around when you do so, or you can apply the left-hand rule to the direction of the B field lines changing, and that will give you the direction that the E field lines are swirling. If you point your thumb in the direction of the change, and your fingers, if you use your left hand, will swirl in the way that the electric field lines will go. Right. The second Maxwell's equation in words simply tells us that magnetic flux lines cannot emerge or converge into a given location, which means that they cannot start or stop. If they cannot start and stop, the only possible solution is to have loops or circles or ovals or something that closes back onto itself. And finally, the fourth equation, which will be the curl of the magnetic field H, will equal to a sum of two things. The first is the current density J plus the time derivative of the electric flux density with respect to time. And we can put a 0 in right here to create some symmetry, since this J right here is motion of electric charges, and this 0 basically represents motion of magnetic charges or magnetic current. All right, so we got a nice symmetry here. A changing magnetic field creates swirling electric fields, and changing electric flux lines make swirling magnetic fields. From Maxwell's equations, we can derive what's known as the wave equation, which, if we assume a few things, we assume J equals 0, that there's no more sources, and that also implies that there's no charges, rho v equals 0. We also can assume that mu and epsilon are constants. They don't vary with location, they don't vary with electric field, they're just straight up numbers. They can be complex numbers, but they're still numbers. When we do that, then we can come up with the wave equation, which is that the second spatial derivative, or the Laplacian, the vector Laplacian of the electric field, is negative epsilon mu times the second time derivative of the electric field. And we can make the exact same equation for the magnetic field, that the second spatial derivative, known as the Laplacian of the magnetic field, equals negative epsilon times mu times the second time derivative of the magnetic field. There's a squared right there. All right, what this tells us is that the second spatial derivative of the electric field is proportional to the second time derivative of the electric field, and the same can be said for magnetic fields. And from this, we can come up with a solution in which basically you have a moving wave. That is the only thing that can satisfy this equation right here. In particular, we're going to have a wave that will move with a velocity and potentially will attenuate. Right? Now, the solution for that wave equation is more commonly written in time harmonic form, which means that we are assuming that everything is oscillating at one particular frequency and that that frequency is known, and it is omega. If we do that, then we can take this time derivative and replace it with the j omega, since we're basically converting this into phasors. If we do that, then we have that d squared x component of E with respect to z squared equals omega squared times mu times epsilon times the x component of E. If we assume that the electric field is in the x direction. And we can do that because whatever wave we've got, we can just orient our axes such that the x-axis is pointed in the direction of the electric field. If we do that, then the solution to this equation can be determined, and it basically comes out to the following. The x component of E is equal to some base value at the origin times E to the minus j beta z. We are assuming propagation in the plus z direction. And for the magnetic field, it'll be pointed in the y direction, and it's going to be equal to E0, that phasor at the origin, divided by eta times E to the minus j beta z. And you'll notice that there's a clear relationship between the electric field and the magnetic field. The first is that they point in different directions. The electric field pointed in the x direction, and the magnetic field pointed in the y direction. The second is that the electric field equals the magnetic field divided by this function eta, which is equal to the square root of mu over epsilon. We also have this wave number beta, which equals omega divided by the propagation velocity, or it's equal to omega times the square root of mu times epsilon. And this basically describes how the phase is changing with distance if we freeze the wave in time, or if we measure it at different points in time. And this propagation velocity here, Vp, if everything is kind of nice and smooth and not attenuating, then the phase velocity, or the propagation velocity, is 1 over the square root of mu times epsilon. All right, this was for the lossless case, where there's no attenuation. Then everything kind of reduces and we have a cleanly defined velocity. Now this assumes that everything is propagating in the positive z direction, but that will not always be the case. So to have arbitrary directions, we are going to have k hat represent the direction of propagation. In which case we'll write the following. The electric field as a vector will equal to the value at the origin as a phasor times E to the minus j beta times k hat dotted with r, where r represents a vector pointing to the location where we want to calculate the electric field. And the same can be said for the magnetic field. As a vector in the phasor direction will simply equal to the electric field as a phasor at the origin divided by this quantity eta times the same exponent e to the minus j beta times k hat dot r. R again represents a vector to the place where we are observing the electric field. K dot r basically represents how far in the direction of propagation we are when we get to that location. And so e to the minus j beta times that is basically going to rotate the phasor E0 by whatever amount we are, depending on our location, how far up and down the wave propagation we are. So with that, we can now represent a wave with an arbitrary direction. You'll also notice that the electric field crossed with the magnetic field is in the direction of propagation. And that will apply anytime we have a uniform plane wave, which is sort of the simple and most convenient description of a radio wave that we're focusing on in this class. All right. Now we can also add loss to everything. If we add loss to everything, then we're going to calculate an effective epsilon, which will be equal to the real part of the permittivity, the original value that we talked about from the beginning, and we can have an imaginary portion of that, which is reflecting the fact that the dielectric realignment of molecules in a certain material may be inefficient, it may waste energy, it may slow down, it may lag, and that is reflected by this imaginary component of the permittivity. But we also have to account for electric conductivity, which mathematically will come into play in this way, minus j sigma divided by omega. We can take this and basically plug it in to our earlier formulas to calculate the wave number, in which case, instead of beta, we're going to replace beta with j times k, and jk will equal to j omega times the square root of mu times epsilon effective. So we take this formula for epsilon effective. This is just material properties that you can look up for whatever it is you're dealing with, foam or aluminum or any material. And that just plugs straight into this mu times epsilon effective. This jk is sometimes also written as gamma. And we, in fact, use gamma back when we were talking about transmission lines. So you can use gamma or jk as long as you're consistent. But whatever this is, this will have a real and imaginary part. Right? This is going to come out to be a complex number, 7 plus j, 8,000 j plus 0.1 real components. Whatever those are, we're going to have a real and imaginary part. The real part will determine the attenuation in units of nepers per meter, where a neper is a single reduction by a factor of E. And the beta will represent the propagation in units of radians per meter, which means if you step forward by 1 meter, the phase of the electric field is changing by that many radians from where you started. And as the conductivity and the dielectric, the imaginary part of the dielectric grows and grows, what will happen is the attenuation will grow and the propagation will shrink, and eventually they will actually be equal to each other. Right? So for so-called good conductors means it's got a lot of conductivity or maybe a lot of dielectric loss, which means it's very poor at allowing radio waves through. But in the good conductor regime, we're going to get that alpha equals beta equals the square root of pi times f times mu times sigma, in which case we're going to find something called the skin depth, which equals 1 over alpha, or 1 over the square root of pi times f times mu times sigma. So even in a good conductor, like metal, for example, which by and large reflects a radio wave and doesn't actually allow any penetration into it, in reality, there is a small amount of penetration into the material, and it's basically defined by the skin depth. Right? The skin depth tells you how far into the material you go, before the electric and magnetic fields are going to reduce by a factor of E. And if you go 2 skin depths, they'll reduce by a factor of another 1 over E, which means 1 over E squared. In that case, we also have this intrinsic impedance eta, which equals the square root of mu times omega divided by sigma, and this works out to be approximately E to the j times pi over 4 is going to be its phase. So there's going to be a 45-degree phase shift between the electric field and the magnetic field in a good conductor, like, for example, metal, or seawater is also a good conductor at most frequencies. You have to go very high in frequency before seawater is not a good conductor. All right, so with that, we can leave off this crash recap of wave propagation, and we'll move on to talk about the power flow. Since having described electric fields and magnetic fields, we really would like to talk about energy and power.